So, hello. Can you hear me, Soham? Hello. Can anyone reply to me? Am I audible to you?
Yes, sir.
Okay. We have a very less number of students today. So, how many of him? Only Soham is there today. Okay, that's fine. Okay. Even if there are two sessions, I think the number of students we have is too many. That's why we had this two session concept, but I think not many are joining this live session. Okay, that's fine. Anyways, these recorded sessions will be available to you on YouTube. So let's begin with the uh, live session week 2 of the NPTEL course design of reinforced concrete structures. And so today we will be mainly talking about what we will be talking about the partial factor of safety. So, what is partial factor of safety? Usually, we use this partial factor of safety in limit states of method, and as we can see here, we have partial factor of safety for two things. That is, either we apply the partial, not either we apply it for both, that is to the material as well as to the load. So partial factor of safety, you must have seen the week 2 content and the week 3 content up to now. And let me just switch on to this pen mode. Okay, so fine. Here you can see we have these two curves. The first one is the characteristic curve and the other one is the design curve. So basically we have partial factor of safety for load, and the other one is for what? Other one we have it for material, or we can say it just for strength. So when we talk about partial factor of safety, what partial factor of safety do we apply to load? To load we apply a partial factor of safety which is multiplied to the characteristic load, and the other one is being the characteristic strength, that is material what it will provide to us, it will provide us with strength. So material, it will give us a strength. So what type of partial factor of safety, what we will be doing with the material characteristics, that is just to get to apply the partial factor of safety to material, we will divide the characteristic strength with the partial factor of safety. So what we can say to find the okay, so we have Albert here. Okay, fine. So I have just started with the concepts of partial factor of safety. So factor of safety, it can be applied to both load as well as to material. So when we talk about load, the partial factor of safety is multiplied with the characteristic load, and when we talk about material, that is the material, it will give us strength. So the partial factor of safety, it will be divided by the strength. So what can we say to find the design load? So design load, we can find it by multiplying the characteristic load multiplied by partial factor of safety. While what can we say, what is the design strength? Design strength is nothing but characteristic strength divided by partial factor of safety. So you all have already studied this from the normalization curve, like what we have here. This is the bell shaped curve, and when we talk about the loads, what can we say? Not more than 90%, 95 percentage of the load exceeds this value. And when we talk about the material strength, what we say, not more than 5% of the material strength, it falls below this value. So what basically we do in limit state method is we design for these two criteria, that is we design for the uh, ultimate load, and we design it for the design strength of the material. So that's what we can see over here. So this is a typical stress strain curve for Fe415. So here we can see the characteristic curve. So the characteristic curve, what it does, it says characteristic curve, we got it. What we can say, that is this strength of the material will not fall, not more than 5 percentage of the test results will fall below this characteristic value. Now, how did we get this design curve? So it's very easy to get this design curve. How can we find this design curve? We can find this design curve very easily by dividing this characteristic strength by the partial factor of safety. So can any one of me tell me what is the partial factor of safety for steel? Can any one of you tell me? Maybe Sridhar, or maybe Albert. What is partial factor of safety for?
1.78.
Can you repeat?
1.78.
Okay, so it is not 1.7. What partial factor of safety we take it for steel is 1.15. So it is very important to know these values. For steel it is 1.15, for concrete it is 1.5. So again I am repeating for the newcomers. What I have discussed up to now is I have discussed about the characteristic strength, and I have discussed about the design strength. So what is characteristic strength? Characteristic strength is nothing but the resistance provided by the material. It is the resistance provided by the material, that is we get it by testing many number of samples, and not more than 5% of the characteristic strength it falls below a specific value. Then how do we get this design curve? With the design curve we obtain it by dividing the characteristic strength with partial factor of safety. I hope this is very clear to you. This is a very important concept, and you will be needing this throughout the course of RCC. So I'm so now it should by now it should be very clear that two we have two things. The first one is the load, and the other one is the material. So material, what does it do? It provides us with resistance. Load is what? Load is coming from some external live load or dead load. What can we say? From some external source load comes, and for that load it will be resisted by the material. So now let's start up with this design strength of steel. So we have this characteristic curve, we have this design curve. Now let's understand what all are this. So here you can see that firstly when we load the steel, uh, Kiran, are you trying to speak anything? Okay, I think that was by mistake. Okay, so what happens when we start loading the steel bar or the steel material? What happens is initially we see a linear zone of the steel. Thereafter, we see a non-linear zone. Then there is a constant stress that we see for increase in the strain value. So here we can see that for firstly we have a linear zone, then we have a non-linear zone, then a constant strength value. So now here is a very important thing you should be knowing this, that is in the linear zone when I apply the load and afterwards when I release the load, what happens is the steel comes back to its original zero, that is there is no deformation, it comes to its original zero. But as soon as it enters into the non-linear zone, so for example it has reached to this point. So when it reaches to this point, and now when I reload, or what can I say, when I remove the load, after removing the load, I will be seeing that not 100 percentage of my uh, strain value is recovered. That is, there is some residual deformation which has left into my bar. So that residual deformation, it is known as what it is known. Because of that residual deformation, what we get is we get inelastic strain. So this inelastic strain, it is not recoverable, whereas elastic strain, which is because of this linear zone, it is recoverable. Okay, so that's fine. So now you should be very confident about these two concepts. That is, when we load a bar, what we know, when we load a bar, we will first be having an elastic region, then an inelastic region, then the strength will be constant. So suppose I have loaded my bar up to this point. Okay, now when I'm loading my bar up to this point, what two deformations will I have? I will have elastic deformation, and the other one, what will I have is inelastic deformation. So for elastic deformation, I will be having elastic strain, which I can get directly from the linear portion of my graph. And the inelastic strain, it is measured through experiments, and these are the inelastic strains which are been given. So if you are following me, can any one of you answer me? The design stress is this, and there is no inelastic strain, zero inelastic strain. So what does this mean? I already told you, when we load a bar, we have two types of deformation. First one is the elastic strain, and the other one is the inelastic strain. So if inelastic strain is zero, whatever deformation we have is the elastic strain. So what does that mean? That mean, like, we have loaded our bar only into this elastic region. So that simply means this. So as I load our bar further, what can I see? The inelastic strain, it goes on increasing. So this is the only inelastic strain value given to me. And apart from this inelastic strain, I don't have, or the elastic strain, it is not given up here, but you can calculate it very easily. We will be seeing this all in further slides. So for example, if we have this 0.85 FYD, so what is FYD? FYD is nothing but design yield strength. How can we get the design yield strength? Can any one of you tell me? So this is FYD. Okay, so FYD, this is design yield strength, and this whole ratio, it will give me elastic strain. When I add this elastic strain with inelastic strain, what I will get is, I will get the design strain, that is the total strain in my bar. Okay, fine. I think things will get more clearer when I take the problem in the coming slide. So let's move on to the problem. Okay, so we have this problem over here. So let me read out the problem first. Inelastic strains corresponding to the various stress levels in the design stress strain curve of Fe 550 grade steel is given in the table below. FYD represents the design yield strength with partial factor of safety 1.15 with respect to the characteristic strength. So these are the inelastic strain. I already told you we cannot find the inelastic strain directly, but the inelastic strain which is given over here, it is found it through experiment. So these are the inelastic strain for various design yield strength of FE 550 bar. So now what they are asking us to do, they are asking us to find the stress values in the design stress strain curve of the given steel corresponding to the following strains. That is, firstly for 0.0015, then all of these values as you can see over here. So let's now firstly revise the concepts again so that it would be easy for you to solve this problem. So here you can see the curve again. So we have a elastic zone here, this one. So this is the elastic zone, this is the inelastic zone. Because of this inelastic zone, we have inelastic strain, and because of this zone, we have elastic strain, and all of the elastic strain, it get recovered once we remove the load from our bar. So now it is just listen to me, this is a very important concept. For example, just pay attention here. What I have shown you, I have shown you that there is zero inelastic strain over here. Okay, so zero inelastic strain, there will be some elastic strain for this value. Definitely it will have some elastic strain, but there is no inelastic strain. So whatever elastic strain which corresponds to this stress value, any stress which is less than this elastic strain value, it will be belonging to this elastic zone. So the strain what we can find from this elastic zone, it can be directly found out by the slope of this graph or directly by this formula. There is this value is 0, for which case for any strain or for any stress which is falling below this value. Okay, or what can I say, for any strain which is falling less than the strain belonging to this stress value. Okay, so if you all have, and I know this is a bit of confusing, if you all have any doubt you can ask me, but I can make you pretty sure that with the problem coming up in the further slide, things will get more clearer. So I just want to confirm you that when the strain it belongs to this linear zone, what happens is when the strain belongs to this linear zone, we can find out directly the elastic strain by this formula. But for the stresses which are falling in this nonlinear zone, we have some strain values for some of the points in this nonlinear zone. And suppose if they are asking us to find a stress value belonging to some point which is in between these two known points, then we need to do the linear interpolation of these 2 points, and then we can find this value. Okay, and further, if our elastic strain it belongs to some value over here, or I think I should point out here the design curve. So if I have some value over here, the what will be my design stress, it will be constant. So any strain which is in this area, any strain which is in this area, it will be having a constant stress value, as you can see here. So let's now solve the problem. I don't know, there is no response from any of you, but I think since the audience are also very less, and you people are just coming and going from time to time, so it would be beneficial for you if you stay in only one of the live sections going on now and pay attention to one of the live sessions. So that would be more beneficial for you. So here I have already told you there are some inelastic strain given for some design stress values. So let's see how can we find the stresses corresponding to this strain. Okay. Okay, so let's move on to the further slide. So here, calculate the design stress and the strain values at the given stress levels. So these are the given stress levels and these are the inelastic strain for this. Okay, so how can you find the design stress value from this? Can any one of you tell me? How can we find the design stress value from this? It is very easy. Design stress value will be nothing but zero point 0.8 times Fy divided by 1.15. Okay, so that will be the design stress. And what will be the total strain? What will be the total design strain? The total design strain is nothing but elastic strain plus inelastic strain. This is what, this is a very important concept and you guys should pay attention to this. Elastic strain plus inelastic strain will be our total design strain. So from where I will get the elastic strain? I will get the elastic strain from the design stress. And inelastic strain, I have already told you we cannot find the inelastic strain because in nonlinear zone we have no control or we have no particular formula. But in an elastic zone I can find the elastic strain by the slope of that curve, and inelastic strain they have provided us with these values. So what will be the design stress? Design stress will be nothing but zero point 0.8 times Fy by 1.15. Okay, what is Fy? What is Fy? Fy is 550. I have to find the design stress for Fe 550. So these are all the design stress. You all can like use your calcs and find out this value. It will be good if you do this in the live session only. So these are the design stresses. And now how can I find the design strain? Design strain, it corresponds to two value. I am repeating this again and again. So it is a addition of elastic strain with inelastic strain. Elastic strain, how I can find elastic strain? I can find out by dividing the design stress value with elastic modulus of steel. Okay, and when then after adding it with inelastic strain I can get the total design strength. So these are the formulas. You can all substitute these values in this formula and you can find out the value. So I don't know whether you are doing it or not, but uh, it's fine. The recorded lectures will be available and you can do it afterwards also, but I would encourage you to do it now only. However, I have calculated all the values and I am displaying all that values over here. So these are what? These are the design stresses, and these are the design strains. Okay. So we have the design strain value for these stresses. Okay, for these stresses and for these strains. Now in the question, what they are asking in the question, they are asking me to find they're asking me to find what is the stress value corresponding to these strains. Okay, they are asking me to find the stress values corresponding to these strains. So what are these? These are all design strains. So we already calculated the design strains over here. So we have some value of design strains, we have some value of design stress corresponding to these design strains, and now we have to find some design stresses for some particular value of design strains. So let's look on to the further slide. Okay, so here I have shown you three important points which I have already explained you in the previous slide, that when you have a stress strain curve, and within the stress strain curve of steel, what you have a linear zone, then you have a non-linear zone, and then the constant zone. Okay, so I have told you, the question asks you to find a stress value corresponding to a particular strain value. So we have some sets of design strain which we have calculated, we have a set of design stress corresponding to this design strain. Okay, we have some values, we have calculated it in the previous slide. So these values, they lie in different portions of this graph. Let me mark some random points for you. Okay, now this design stress, they lies over these points in the graph, and they correspond to some strain values. Okay, they corresponds to some design strain value like this. Okay. Now the questions asks us to find some design stress values for some design strain values. So for example, our strain value lies over here. So I can easily identify this strain value is less than this strain value. That means this strain value lies within the linear portion of my stress strain graph. So when it lies in the linear portion of my stress strain graph, I can directly find the stress by using this formula, that is by using the slope of this graph, because this is the linear portion. Now suppose my strain, it lies in between these 2 points, that is in the linear zone. So between these 2 points I cannot use this formula. So what I need to do, I need to do the linear interpolation, that is this one. I do the linear interpolation between these 2 points to find the stress value for this. Okay. Now, what would be the third case? Now, for example, my design stress lies in this zone between these two strain. Can any one of you reply me, or just unmute yourself and tell me what will be the design stress value corresponding to a point which is lying between these 2 points? For example, the stress value for this is Fy. Can any one of you tell me? Okay, I think we have a very shy audience today. No one is replying to me. That's fine. So I already told you, if I have a strain value between a point which is belonging to this constant region, then strain any stress belonging to this strain will be a constant value Fy only. So all of the points which is lying on this constant region, it will be having same Fy value. Okay, so that Fy value is nothing but our design yield strength of my bar. So now let's look on to the answer of this problem. I think I have pretty much tried to explain my best how we are proceeding up with this problem. So now we have this, we already calculated these values in the previous slides. I have displayed a small version of this slides for your reference purpose. So now what we need to do, we need to find the design stress value corresponding to a strain of 0.0015. Okay, so this is the design strain. So you can see, you can compare this design strain with one of these strains for which the stress value is available. Okay, so 0.0015. So, can anyone of you want to try this 0.0015 value? Is it less than 0.0019? At least reply to me this. Is 0.0015 less than 0.0019?
Yes, sir.
Yes, right. So, what does that mean? What does that mean? Here you can see there is zero inelastic strain for strain corresponding to this point. Okay. So, zero inelastic strain means Suppose this point is lying over here. So zero inelastic strain means this point belongs to a linear zone of my stress strain graph. Okay. So a strain which is 0.0015, it is less than this value. That means my, for example, this value is 0.0019. My 0.0015 lies at this point. That means we have this point in the linear zone of our stress strain graph. So how can we find the stress value for this point? Come on. What is stress? Apply your basic concepts. It is very easy. We know what is elastic modulus. Elastic modulus is nothing but stress to strain. Stress to strain. This is true only when we are in the linear zone. This is nothing but the slope of this graph. It is very easy. Okay. So we have 0.0015 which is lying in the linear zone of this graph. So we can calculate the stress value directly. We know E of steel. What is E of steel? 2 into 10 to the power 5 MPa. Then we can multiply it by the strain is 0.0015 and we can get the stress value. That's what it is done over here. It's very easy. Okay, are you getting me? Okay, that's fine. Now we need to calculate the stress value belonging to 0.002. Okay, 0.002. So now 0.002, it is lying between these two points. Okay, and between these 2 points we already know that only this is the point up to which our graph is linear. After this point we have a non-linear zone. Okay, so now what we can say, 0.002 lies between these 2 points and it is in the non-linear portion of the graph. So what, how can we find the design stress? I just explained in the previous slide. When our point lies between 2 points which are in the non-linear zone, how we can find the design stress? Simply we need to do linear interpolation. So the formula for the linear interpolation, so it is a very basic mathematics. You can do it. If we have a, if we have 2 points and we have a point in middle, suppose this is x1 and this is y1, this is x2 and this is y2, and for the middle we have x and y. So if we have this x1 and x2 y2 and x1 y1 known by linear interpolation, I can easily find the value of x or value of y, any one of them being known. So that is what I have done over here. Similarly, for 0.0025, now 0.025, it lies between these two. Okay, so again we can do the linear interpolation and find the value. I have not like calculated it again and again and shown in the formula, but I'm pretty much sure it is basic mathematics. Only the purpose of this problem was to clear up your concepts of the stress strain graph of the steel. Okay, now the third one being 0.003, again it lies into the non-linear zone. Now the fourth one is 0.0035. Okay, 0.0035, again it lies between these 2 points. So again we need to do the linear interpolation. What is the last one? Last one is, so what I explained you previously, I explained you that we have a linear portion, we have a non-linear portion, then we have a constant value. So the point at which our constant value starts, that point is nothing but 1 times FYD. Okay, now 0.00439 corresponds to the design strain of this point. After that point any strain will have a constant FYD. So 0, now we need to find the design stress for 0.0045 strain. So 0.0045 strain, it is greater than this value, that means it lies in this portion of the graph. So now can any one of you answer me what will be the design stress for the strain corresponding to 0.0045? Come on, this is very easy. 0.87 FY. 0.87 FY, very good. Okay, I think by now some of you have cleared your concept. So just it is a simple mathematics. You have a linear, you have a non-linear zone, and you have a constant zone. So I have not displayed the answer over here. So this is 0.87 FY value. Okay. Come on. So this was the end of this problem. Any one of you, if you have any doubt in this problem, you can ask me right now only. So today, basically, I was taking problems on partial factor of safety. The reason behind taking this problem is you should be very clearer about the partial factor of safety which we are using in the widely used design philosophy, that is the limit state method. So in limit state method, what we do? Let me again revise. What we do? We apply factor of safety to both material as well as to load. So to apply partial of fact, that is the reason it is called as partial factor of safety, because a part of factor of safety we applied it to load, and a part of factor of safety we applied it to material. So while applying the partial factor of safety to load, what we do, we multiply the characteristic load with partial factor of safety, and while applying it to material, what we do, we divide the characteristic strength with the partial factor of safety. I think by now it would be clear to you all. So now let's move on to the other very interesting partial factor of safety of load. So this is the partial factor of safety which is being applied to load. Okay, so for loads we have different types of loads. So we have dead load, we have live load, we have wind load. And wind load, we interchangeably use it for earthquake load also, because the nature of these two loads are more or less similar. So that is the reason the more of this value we use it, or the higher of these two loads we use it for design calculations. So in IS 456 2000 table 18, we have the various load factors. So what are load factors? What are load factors? Load factors are nothing but it is the partial factor of safety which we multiply it with the characteristic load to get the design load. Okay. So load combinations, we use the load combinations in this manner. So first we have the dead load plus live load. So you can see it over here, both of them have a partial factor of safety of 1.5. Then we use this all three loading condition for our design purpose. So we need to check our design for all of these three loads. Okay, so uh, these are some design load combinations which we must do before carrying out any design. Then the second one we have is dead load plus wind load, and the third one we have is dead load plus live load plus wind load. And for the third case we have 1.2 for all of three of them. For the second case we have 1.5 or zero point 0.9. So zero point 0.9 is basically because of load reversal, and it is mentioned over here. So load reversal during the time of earthquake loads or wind load, what we can have is we can have negative impact of the dead load, and that is the reason the dead load may be the effect of dead load may be neglected during such load reversal time, because what we assume is we assume the beneficial effect of dead load, but that beneficial effect may not be available for us during the stress reversal phenomena which is going on into the structure during some activities such as wind loads or seismic activities. So basically these all were load factors for limit state of collapse. Now what we have another one, limit state of serviceability. So I think you all must be knowing this. We have limit states in two way. We have limit state for collapse, and the other one we have is limit state for serviceability, or what we can see, we have limit state for deflection. Okay, so collapse, what we do, we design the limit state of collapse for torsion, for compression, for tension, for flexure, and what else? Torsion, compression, tension, flexure. What comes with bending? Shear, yes, very good. So these are all the limit state of collapse for which we do this load calculations. And the other one is limit state of serviceability. So limit state of serviceability is nothing but deflection criteria. So either we do it for the safety purposes to check out the deflections. So now let's look out some problem for this design loads also. We have already looked out one problem for design strength by applying partial factor of safety. Now we will be doing the partial factor of safety thing to load. So this is the problem which is being displayed over here. Okay, so let me read out this problem for you. A vertical slender reinforced concrete column 4-meter high is subjected to the following load in addition to dead load of 40 kilonewton. Okay, now an imposed load of 50 kilonewton, it can be seen over here. Then what we have, just a second. Okay. Then what we have is we have a horizontal wind load of 3 kilonewton per meter along the height of the column. Okay. So we have a dead load of 40 kilonewton. We have a imposed load that is a live load of 50 kilonewton. And in addition to this, we have a wind load which is 3 kilonewton per meter, which is acting along the height of the column. So this is the given dead load. We have a live load. We have a wind load. Now wind load is given in a unit of kilonewton per meter along the height of the column 4 meters. So how can we calculate the wind load now in kilonewton? Wind load, it is acting along the height of column. 4 meter is the height of column. Suppose this is the column and the wind load is acting like this. This is our wind load 3 kilonewton per meter. So what would be the effective load? Effective load will be nothing but multiplying the UDL type of wind load with our total height of column. 3 into 4, that is 12 kilonewton. So we have dead load, live load, and what the problem is asking us to do, determine the design loads for all load combinations for strength or ultimate limit state. So for strength or ultimate limit state means it is asking us to find the load combinations using what? Using limit state of collapse. So we need to use, so what we need to use, we need to use all of this, we need to find all of these three combinations. Okay, so let's look at them. So let's first find for the first case. First case we have dead load plus live load. So we have the partial factor of safeties as 1.5 plus 1.5. So dead load we have 40, live load also we have something 50. So I have found out the first load combination. Then the second load combination is for dead load and wind load. So wind load is nothing but horizontal load while dead load is vertical load. So horizontal load 1.5 plus 1.5. Okay, so we have this one. Now in the case 2 I have shown you, because of load reversal we have another case. So for that another case also we have calculated the two loads, zero point 0.9 times the dead load and 1.5 times the wind load. Okay, so you can add them both and find the, here also you can add them, 78 kilonewton. Now let's move on to the third case. Third case is nothing but the combination of these three: dead load, live load, and wind load. So the factor load factors are 1.2 for all of them. So the vertical load I have calculated it separately, and the horizontal load also I have calculated it separately. So you can add them both and find the load combinations for this design. Okay, so this was all about today's live session. These were the two problems I was like willing to show
Sir,
you. Yes.
sir, these load combination, where means in the design, where we have to use which load combination?
No, it's not like that,
No,
Shivam.
it's not like that.
Firstly, we need to see the worst load combination for that, and actually, what softwares normally do, I will tell you. Softwares, what it will be do, it will be like calculating all the load combinations, and what it will do, it will find the worst out of this load combination, and for that worst case, it will be designing our building.
Sir, I want to ask if there is in a multi-storied building when we will use the wind load condition,
Wind load,
uh,
yeah,
or means there must be some limit earthquake or wind
yes,
means
yes.
for five floors we may do not require to do earthquake analysis or something like that.
Yes, yes, yes,
Yes.
definitely. There is one IS
So
code.
what is the criteria?
Yeah, we have a IS code IS 875 Part 3 that is specifically for wind load. So you can check out that code and see what are the various criteria or what are the various height of the building for which the wind load is to be considered. And we have codes for earthquakes also. So earthquake load and wind load, although the way in which these two loads act, the phenomena in which these two load act is the similar, but earthquake load we only use it in the area where the magnitude of the earthquakes are beyond or in India usually have, we have different zones of earthquake. So depending upon that different zone, we design our building for earthquake loads. Whereas for wind loads, we have velocities of wind corresponding to different areas. That also you can find in IS 875 part 3. And the different zones of earthquake, you can find it in IS 1893. Okay, so you can check out these two codes for earthquake load and wind load. And in these two codes, the various design criterias and the various types of buildings for which these two loads are to be considered are explained in a very well defined manner. Was I able to answer you, Shivam?
Yes, yes, sir. And sir, one more thing means in a structure which has more number of floors and a structure which has less number of floors. So in that case, when we need to do the earthquake analysis, if there's less number of floors, then we do we need to do an earthquake analysis?
Shivam, it's not about when you talk about earthquake load, then the number of floors you are saying, that doesn't matter. If that building it is lying in some earthquake zone, which is having a very high impact of earthquakes in that zone, then you will have to definitely design your building for earthquake loads. And now I would like to clear it out how the height of building will play a role. Okay, so the height of building would play a role in a manner that if the height of the building is less, it will be having some period of vibration. Or what can we say? For example, we have, okay, so let me explain you. So we have, suppose these three buildings. Okay, so now earthquake has come and these three buildings are subjected to some shaking. Okay, now what will happen? I will have some different frequencies of this shaking. For example, omega 1, omega 2, and omega 3. Now for example, this building have some time period, this building have some time period. So depending upon the different time periods of this building will respond for different frequencies of earthquake. So it can happen like for some earthquakes, this building is under more danger condition. For some earthquake, this building is some under a more dangerous condition, and for some other earthquake, this building is some. So it is not like all of these three buildings will simultaneously fail, depending upon their time period, which depends upon the typically upon the mass and the stiffness of this building. So depending upon that time period, the designing of this building would be done for earthquake. But definitely we will have to go for the earthquake design. It's different for wind design, but for earthquake design we will have to go.
Okay, sir. Okay, sir.
Okay, so it's, I know at this stage it would be not very clear for you, but earthquake designing of buildings is a completely different topic and a very wide branch to study, so that you can explore if you are interested. But for the time being, we are only saying what are the various load combinations that we consider for designing. That's all. Any more doubts? So
Sir, these earthquakes analysis and wind load analysis, these are in structural engineering course.
yes,
Means
yes, yes. This all comes under structural engineering course.
okay, sir.
Yeah, okay. Any other doubt? So I would request you all to, yes, yes, Shiva.
Sir, last week you told about that you will find out why the trapezoidal load.
Yes, yes,
Uh,
yes, yes, Shivam, I remember, but I have not brought the solution for you in this session, because what I decided is I will be like going with the flow of our course content, because I don't wanted to include anything into the middle of the course. So as and when time will come for the trapezoidal load of the slab, or when we will be taking live sections on slab, at that particular time instant I will be definitely explaining you all of your doubts at that time. Okay.
okay, sir. Thank you, sir.
Yes. So I would request you all to just go through these two problems, especially the first one, because it will clear many of your concepts for future. And I think that's all for today's lecture, and thank you for joining. And let's meet on next Tuesday 6 to,
Sir,
yes.
Sir, the third assignment consists of questions which are related to the RCC bridges,
Okay.
and it is not related to DCS.
Okay, I think you should report this in the NPTEL forum. I have no control on the assignments. I can only take the live sessions. If you have any doubt in those questions, I can definitely help you with. But you can just post on the discussion forum like these all problems are not relevant, or maybe the question you see is in terms of design of bridges. You said, na?
Yes,
But
sir. It includes IRC code as well. Things about that.
Okay, so I think one or two questions may be for that purpose, so that you may get familiar with different codes. But that's fine. I think you can manage with it. If it's difficult, you can come to
No,
me.
sir. It was related to slabs, calculation of the loads on the slabs, and all of the questions were related to the bridges. All of them.
All of them are related to bridges.
Yes, sir.
Okay,
RCC slab design for bridges.
but the week three content is released already.
Yes, sir. It is released and the assignment is also released.
Okay, so what the week three content? I don't think it would be having slabs and bridge questions, but that's fine. I think you can just post this to the forum of that NPTEL site, and let's see what they reply to us.
Okay,
Okay,
sir.
even I will talk to them if you want. Okay, then.
Okay, sir. Okay.
Okay, okay, okay. Then you all can leave if you want, or if you have any further queries. I'm waiting for the last 2 minutes over here.